Look at a train wheel up close and you'll notice something odd. It isn't a flat cylinder. The tread is tapered, shaped almost like a cone, tilted slightly from the inside edge to the outside. That tiny angle, about 1 inch of taper for every 20 inches of wheel, is doing something almost nobody assumes it's doing. A lot of people think the flange, the metal lip on the inside of the wheel, is what steers a train around curves, but it mostly isn't. So, if the flange isn't doing the steering, what actually is? Start with something most car drivers never have to think about. A car has a differential. When you turn a corner, the outside wheels need to cover more ground than the inside wheels in the same amount of time, and a differential lets each wheel spin at its own speed to make that possible, silently, under the floor of the car, without the driver ever noticing it's there. It just works. A train doesn't have anything like that. 2 wheels on the same axle are welded to a single solid shaft. They can't spin independently, not even a little, with no clutch or gearing of any kind to let one side turn faster than the other. Whatever speed the left wheel turns, the right wheel turns at exactly the same speed, always, on every curve, for the entire working life of that axle, which can run for decades. That creates a real problem the moment a train hits a curve. The outer rail on a curve is physically longer than the inner rail, the same way the outside lane on a running track is longer than the inside lane, measured all the way around the bend. On a sharp curve, that difference isn't trivial. If both wheels on a rigid axle were perfectly flat cylinders, identical diameters front to back, one of them would have to slip. Either the outer wheel scrapes along, unable to cover the extra distance it needs to, or the inner wheel spins in place, unable to slow down to match. Neither option is good. Both mean grinding, friction, and wear on a scale that would eat through wheels and rails constantly, curve after curve, on every single trip, on every single railroad in the world. The cone shape solves this without needing a single moving part, and it does it almost too simply to believe at first. Because the wheel tapers, its effective rolling diameter isn't fixed. It depends on exactly where the wheel is touching the rail at that instant. Push the wheel set slightly toward the outside of a curve, and the outer wheel starts riding on a slightly larger section of its own taper, while the inner wheel shifts onto a slightly smaller section. Larger diameter means more distance covered per rotation. Smaller diameter means less. Even though both wheels are still spinning at the exact same rate, welded to the same rigid axle, they're now covering 2 different distances automatically, purely because of where the cone happens to be touching steel. No differential required, no moving parts, just geometry, quietly doing a job that would otherwise need real mechanical engineering to solve, using nothing more than the shape of the metal itself. A German engineer named Johannes Klingel worked out the math behind this self-centering effect in 1883, more than a century before most of the trains running today were ever built, and decades before anyone had a practical use for automobiles at all. What he proved was that a conical wheel set doesn't just tolerate being pushed off-center. It actively corrects itself. No motor, no sensor, just geometry doing the correcting on its own. Push the axle slightly to one side, and the geometry alone steers it back toward the middle of the track, the same way a marble settles into the bottom of a bowl, without anyone guiding it there by hand. That correcting force is happening constantly, on every stretch of track, whether the train is on a curve or running dead straight, and almost none of it involves the flange touching anything at all. Here's the part that actually answers the question. In completely normal running, on straight track, and on most curves a train encounters, the flange never touches the rail at all. It hangs there with a small gap, doing nothing, existing purely as insurance against a problem that hasn't happened yet. The cone does the real work of keeping the wheel centered and steering it through gentle curves, using nothing but the changing contact point between tapered steel and the rail beneath it. The flange only earns its keep when something goes wrong. A curve tighter than the geometry can handle on its own, a gust of crosswind, a moment of genuine instability, and only then does that metal lip make contact, acting as a last resort guardrail instead of the primary steering system everyone assumes it is. Most of a wheel's working life, that flange is just along for the ride, never once called on to do the job its shape suggests it exists for. Now here's why nobody just made the wheels flat and called it a day. A flat, cylindrical wheel would need the flange to do all of that steering work, all the time, on every single curve, because a flat wheel has no way to change its effective rolling diameter no matter where it sits on the rail. It can't adapt. It's the same diameter everywhere, so the only thing left to force it around a bend is brute contact. That means constant metal on metal rubbing between flange and railhead, on every curve, on every train, forever, mile after mile, for the entire lifespan of the equipment. That kind of contact chews through both the wheel and the rail at a rate that would make railroading absurdly expensive, and it raises something more dangerous than cost. A flange that's constantly grinding against a railhead is a flange that's constantly at risk of climbing up and over it, which is one of the most direct paths to a derailment there is. Investigators studying derailments still look at flange climb angles and contact forces today, decades after the underlying physics were first worked out. Running the same calculations, Klingle's successors refined over generations, because that failure mode never fully went away. It just got rarer. The cone does more than refine the ride. It stands between normal operation and the flange doing a job it was only ever designed to do occasionally, a job it's structurally poor at doing constantly. But this elegant trick comes with a genuinely strange cost of its own. The same conical taper that lets a wheel set self-center also gives it a tendency to overcorrect and push the axle off-center, and it doesn't settle politely back to the middle. It swings past center, corrects again, overshoots the other way, and settles into a rhythmic side-to-side motion that engineers call hunting, a name that dates back to the earliest days of railway dynamics research. At low speed, hunting barely registers, just a faint sway most passengers never even notice, easy to mistake for ordinary track noise. At high speed, it can grow instead of fading, turning into a genuine stability problem that shakes the whole vehicle, rattling everything inside it. The very geometry that makes a train track itself through a curve is the same geometry that can make it sway itself into trouble at speed. And there's no way to fully separate the benefit from the risk. They come from the exact same taper, the exact same handful of degrees cut into the metal. There's a practical side to all of this that most passengers never see. Railroads don't just trust that a wheel's cone angle is still correct. Inspectors use a simple tool called a wheel profile gauge, essentially a precisely shaped template, pressed against the tread and flange to check whether the actual metal still matches the design curve it's supposed to have. It takes seconds per wheel, and it happens on a fixed schedule regardless of how the train looks or sounds, whether it's a quiet commuter set or a mile-long freight train fresh off a mountain grade. Wheels wear unevenly over months of service, picking up flat spots, hollow patches, and subtle changes to that critical taper every single day they're in use. A wheel that's drifted too far from its intended profile doesn't announce the problem with a warning light. It just quietly becomes worse at the one job it was shaped to do, which is exactly why the inspection has to happen on a schedule instead of waiting for something to go wrong first. The taper itself isn't arbitrary either. Railroads didn't each pick their own random angle and hope for the best. Standard gauge railways converged on that roughly 1 in 20 ratio because it sits close to the sweet spot Klingle's math describes. Steep enough to self-center reliably on the curve radii most railways actually use. Shallow enough that hunting stays manageable at the speeds those same railways typically run. Change the ratio even slightly and you're nudging every train on that network toward one failure mode or the other, which is exactly why wheel profile standards get treated as seriously as they do by engineers who will never personally ride the trains they're designing wheels for. None of that changes the underlying trade-off though. There isn't a version of this that eliminates the problem for free. There never has been, not in over a century of trying. A shallower cone angle calms the hunting tendency down and keeps high-speed trains more stable, but it also makes the wheel set worse at negotiating tight curves, since a gentler taper produces a weaker self-centering force. A steeper cone angle does the opposite. Sharper curve performance, but a stronger tendency to hunt at speed. There's no angle that wins on both fronts at once. None. Every real wheel profile in service today is a compromise, chosen on purpose, not a flaw someone forgot to fix. Every train running today sits somewhere on that spectrum, and the choice of exactly where gets tuned deliberately to the specific mix of curve radius and top speed that railroad actually runs. That tuning looks different depending on what the train is actually built to do. A slow freight train grinding through tight mountain curves at modest speed can afford a steeper cone angle, trading a little high-speed stability it will never need for sharper curve taking it uses constantly, curve after curve, all day. A high-speed passenger train built to run flat out on straighter, more gently curved track can afford a shallower angle, trading away some curve agility it rarely needs in exchange for the stability that keeps hunting from ever becoming a problem at speed. Neither train is using the wrong wheel. They're solving two different versions of the exact same equation, just with different numbers plugged in depending on the job. High-speed rail pushes this balancing act to its absolute limit, further than any other application of the same basic idea. At the speeds a modern bullet train operates at, wheel profiles have to be held to extremely tight tolerances, because even a small amount of wear changes the effective cone angle and can nudge a stable wheel set toward hunting territory, without any warning beyond a slight change in ride quality. That wear happens constantly and predictably, which is why high-speed rail operators run wheel grinding programs on a regular schedule, shaving the wheel treads back into their original profile before wear has a chance to destabilize anything. The same grinding happens to the railheads themselves, for the exact same reason, on a parallel maintenance schedule that never really stops. Fractions of a millimeter, checked constantly, to keep a 19th century geometric trick working safely at 21st century speeds. So the next time you watch a train glide through a curve without a screech or a lurch, that smoothness isn't the flange earning its reputation. It's a slight taper, worked out mathematically before cars had windshields, quietly steering hundreds of tons of steel through a bend using nothing but the shape of the metal itself, unnoticed by nearly everyone riding on top of it. The same shape that makes that smooth curve possible is also the reason engineers spend so much effort keeping wheels ground to precise tolerances at high speed, checking, grinding, checking again. One elegant trick, one built-in cost, permanently bundled together in a few degrees of taper, inseparable from each other since 1883. So here's the question worth sitting with. If the part everyone assumes is doing the work is actually just a backup, and the real solution is a shape so subtle nearly nobody would ever notice it unless someone pointed it out, how many other things are we crediting the wrong part for?